Hello, everybody. So what we're going to be looking at today is section 2.2 in the book, which is vectors in 3D. So first of all, one thing I want to mention before we get started here is that this name for the section is actually not a very good name at all because we don't even talk about vectors very much. We do a little bit, but not that much. So the main topic is actually just 3D space and how we deal with it, not specifically vectors. All right, so with that said, let's go ahead and get started. So where will we start? With the definition of a three-dimensional coordinate system. Now, this is going to make perfect sense to you, and you may wonder why we're doing it, but it's just really good and in fact necessary in mathematics to define your stuff. So there's no confusion about what you mean. So what we have is the three-dimensional coordinate system, rectangular coordinate system, because we're going to have other coordinate systems pretty soon. Cylindrical coordinates and spherical coordinates, but we're dealing with rectangular coordinates today. So the three-dimensional rectangular coordinate system consists of three axes, perpendicular axes, I should say, perpendicular axes. You can guess what they are, right? X-axis, Y-axis, Z-axis. And then each axis is a real number line, going from 0 to 0. So each axis is, what did I say? I don't know what I said, but is a real number line representing negative infinity up to positive infinity, which is this is just generally how we have been doing. This is just how you would want to do things. It's how we do things in 2D already, and we're just adding a third dimension. Okay. Now, one thing we will say is that we refer to this as R3. So we refer to this set of 3D coordinates as R3 this way. So it looks like an exponent, but of course it's not. It's just denoting that we're in three dimensions, right? This would be as opposed to R2, which is the set of two-dimensional coordinates, or just R, which is the set of real numbers. So this is the set of real numbers. This is the set of pairs of two real numbers. So like x comma y is R2, and R3 is x comma y comma z, pair of three, a set of three different real numbers. All right. So that's how we define our axes. Now, the thing about this is that there's actually two different ways to do this. So technically, we could do one of two different things. Oops, I erased one of two things. I mean, there's more than two things a person could do, but specifically what I'm talking about this time is this. So we could set up our axes like this. So straight up, and then over here, and then over here. And so this is a right angle, and also this is a right angle, and this is also a right angle, right? So three different right angles. And we could take that and we could say that that this is x and this is y and this is z, right? And I'm labeling it in the positive direction, right? So this is the positive y, this is the positive z, and this is the positive x. Okay? Now, but that's not the only choice, because we could have set it up so straight up over to the left, and then out this way, I guess. And again, right angle, right angle, right angle. They're all at right angles to each other. And I could do this is x, this is y, this is z. And again, this is plus and plus and plus. And the thing is that these are actually fundamentally different, because you can't take this picture here, and if you were able to rotate it any way you wanted, right, you can rotate it this way. Like if you could pick up this set of axes and you rotate it that way or that way or that way or that way, no matter how you do it, no matter how you rotate this, you can never make this picture look like this picture, right? If z is pointing up, which it is here and here, then the fact that we have the positive y-axis on the left and the positive x-axis on the right, and here we have it the other way around, positive x-axis on the left, positive y-axis on the right. So xy going left to right, it's x comma y, not comma, just xy. And here going left to right, it's yx. And that makes these two things fundamentally different. So one of them is called the left-hand rule, and one of them is called the right-hand rule, and they're not the same. And it doesn't really matter which one you use, but by convention, we pick one and we stick with it, and everything we do is based on that. Okay, so specifically, the one we use is this one. So these are different. And they're the right hand and left hand coordinate systems. I can't write words. These and left hand coordinate systems. We use the right hand rule, not the right hand rule, the right hand coordinate system. Which one's the right hand coordinate system? It's the first one that we did, and I'll show you why momentarily. So it's this one, this is right hand rule, and this is left hand rule. And I'm going to show you a picture. Let me see. How do I do this? I press the plus. No. Plus. Photo library. Picture. Drag. Put down. Guess it'll have to go on the next page. No, it can go right here. That's fine. No, it's not. It's too small. Pick up. Put it down here. So there you go. So this is the one we use, and they call it the right hand rule because if you hold out your right hand, so this is a person's right hand, and if your fingers curl this way, and first you hit X and then you hit Y as you curl your fingers, then, and your thumb points up, then that is the right hand rule coordinate axes. So when you curl your fingers this way on your right hand, first you hit X, then you hit Y, and your thumb points in the direction of the positive Z axis. Okay. Now, having said that, you're just going to want to remember how to draw it. Right, like this. You put Z straight up, and then X and Y. You do X on the left, Y on the right, and that's correct. Okay, so you do need to draw it right, because clockwise and counterclockwise do mean things later on in this class, and so if you draw your coordinates the wrong way around, then clockwise will be counterclockwise, right? So you got to do it the right way. And the right way is this way. Again, it doesn't matter. It's just this is how we're going to do it. Okay. Now, as far as locating points in 3D space, you can probably do that. The only thing is that it's hard to draw. Let's do one example. Let's say sketch the point. One comma -2 comma +3 in 3D space. So how do you do that? Well, first you need a set of axes. So you have to draw your axes straight up. And it doesn't really matter how you draw this. Like you can draw X this way and then Y this way. Like this is fine. A lot of times you don't want Y pointing like that. You would rather have Y pointing like that. It's just a matter of perspective. You could also draw it like this, where you draw, again, Z is straight up. You can draw Y straight out to the right. And then X could be like this. So it doesn't really matter. Usually you'll draw one of this way or this way. And basically you either pick X to be horizontal here, or you pick Y to be horizontal here. And they're both correct, right? Because going around left to right here, first it's X and then it's Y, first it's X, then it's Y. So those are both right-hand rule. Okay, so we could use either of these to sketch our point. So then what you have to do is you have to think about where are the tick marks on the graph, right? So on X, you have like 1, 2, 3. On Y, you have 1, 2, 3, 4. On Z, you have 1, 2, 3, 4, 5, right? Like this. So now if you're going to locate the point, how would you do it? So what you would do is, let's get a different color here. Our first component is X. X equals 1. So where is X equals 1? So we've got our X-axis right here. So X equals 0 is here. X equals 1, X equals 2, X equals 3, right? So this is X equals 1. So X equals 1 is actually this entire, like, it's like this, right? That's X equals 1. Then we have, what do we have? Y equals -2. Well, where would Y equals -2 be? Well, we've got Y equals 0 is going to be here. Y equals 1, Y equals 2, Y equals 3. So positive Y is this way, +1, +2, +3. So -2 is going to be the opposite direction. So usually there's nothing drawn there. So you have to kind of go 1, 2, right? That's where that's going to be, -2. And when you draw the line that's equivalent to this line, it's going to be parallel to the x-axis. So it's like this, right? Because what we're looking at here, let me just erase this. If you think about it, what we're looking at here, if you think about a two-dimensional coordinate system, right? What am I doing? Let's draw a straight line. Okay. On a two-dimensional coordinate system, if you're trying to draw x equals 1, that is right here, right? That's the wrong color, this color. Right? So x equals 1 is parallel to the y-axis. And then if you were trying to draw y equals -2, you would find y equals -2. So down here, and that line would be parallel to the x-axis, right? And then the intersection there, that's your point. Well, the same thing's happening here, but in three dimensions, it's harder to realize. So this is your x equals 1. This is your y equals -2, right? 1, 2 on the y-axis, and then make sure you draw this line parallel to this line. And then the intersection there, right? If I pick like a dot there, that's not the point we're looking for. That's like the equivalent to this point. We want a 3 in the z direction. So you have to go up 3. So straight up by 3. 1, 2, 3. So here you have to go 1, 2, 3. Straight up. So it's like that, roughly. Um, and so that's kind of how this goes. And they draw this a little bit differently when they draw it in the book. So what they do is let me erase these lines. So the way they would draw this in the book is they go, okay, we are at 1, and then we know we are at -2, which is like this. 1, -2, and then you go up, and then that gets you where you're going. And so like this is really actually kind of like the corner of a box that's like this. Okay. So it's like the corner of a box, and where you have that point. So it's a little bit tricky to draw and get it in the right place. So this was 1. This was -2. And the 3 was the 3, like that, straight up. So they're hard to draw, but this is the point that we're trying to draw. And you do have to kind of pick the right thing off of the list when you're looking on the homework. And it's a little bit tricky, but there we go. So that's how you would draw a point. What else can we say? Oh yeah, so we can talk about coordinate planes now. Coordinate planes. So there's going to be 3 coordinate planes. And what a coordinate plane is if you set one of the variables equal to 0. So the set of all let's say x and y, well, let me say this. The set of all x, y, z, where actually z is 0, is called the xy plane. Right? I mean, that's just the name. And so you would refer to it this way. You would say the xy plane. If you wanted to write it out in set builder's notation, you would say it's the set of, you could say x, y, z, where z equals 0, but you could just say it's the set of all x, comma, y, comma, 0. You can just put in a 0 for z, such that x and y are real numbers. That's the xy plane. And similarly, there's 2 others, right? Because we could do the xz plane. That would be the plane where you have x0z, where x and z are real numbers. Or you could have the yz plane. That would be where x is 0, but y and z are generally not. And y and z are real numbers. So those are your 3 coordinate planes. 3 of them. And what do they look like? I think I have pictures. I do. Drag it over, put it down. And so there are your coordinate planes, right? So if you think about it, if you set the z value to be equal to 0, then you're just stuck on the ground, right? Because the z-axis is vertical. So the ground is the xy plane. And similarly for the others. So like this wall right here would be where y equals 0, right? Because y is this direction. So if y is fixed to 0, then you're nowhere along this axis, so you're just stuck here. But y, x, and z could be anything, which gives you an entire plane where, gives you an entire plane. And similarly for the YZ plane, if x is 0, this is where you live in that plane. Okay, and so those are called the coordinate planes. Generally, they refer to them by name. They just say XY plane, and you have to understand, okay, Z equals 0 there, Y equals 0 there, X equals 0 there. So those are the coordinate planes. Now, the next thing about these coordinate planes is they actually divide 3D space up. If you look at a two-dimensional plane, which I passed up one here, I guess I'll scroll down to it. Here it is. You know that we give names to this area, this area, this area, and this area, right? We call them quadrants. You have the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. Well, down here, if you're looking at the way these planes divide up space, they actually divide it up into 8 different pieces. It's hard to see them here, but like this entire area, oops, don't do that. Stop moving. This entire area here, like this wall, this wall, this wall, that's one section of space. And if you jump over this wall to go back here, you're in a second section of space. And if you jump over that wall back here, there's a third one. Over here, there's a fourth one. And then down below, there's 4 more, right? There's one down here, one over here, one back here, and then one we can't see. So there's actually 8 pieces of space that these planes divide up 3-dimensional space into, and we call them octants. So do I have a picture? I'm 100% sure I saved it, and it's gone now, so I'm just going to go save it again. I'm just stealing these directly from your book. There we go. Let's screenshot. Let's take this picture now. We're going to steal it, and we're going to put it in our notes. It's very slow. Done. Save the photos. Now, hopefully, it's not going to make this all slow. Oh, look at that. It's all jerky. Close it. Open it up again. There's our notes. And it's fast again. Okay. So, octants. So there's 8 octants. There are 8 octants. The coordinate planes divide space up into those 8 octants. So they divide 3D space into 8 sections. But now we can get from the photo library. There they are. So I don't know about like numbering these. Like we number the quadrants. But there's one here, 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 here. And it's just based on the signs of each of the variables, right? Like plus, plus, plus for x, y, z, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, minus, minus, plus, plus, minus, minus, plus, minus. And I guess minus, minus, minus is not shown, but it's in the back. And those are your 8 octants. And I don't know why we would number them. You probably could, but like if you said like, oh, okay, there's a point in the 7th octant, people would go like, well, where is the 7th octant? I don't know what you're talking about. So, just keep that in mind. It doesn't really matter, but there are 8 of them, and that's how they are. They're based on the signs of each of the 3 variables. Okay. Now let's talk about distance. So you know that you can measure distance in two-dimensional space, basically just using the Pythagorean theorem, right? So distance between 2 points in 2D. So if I draw like a set of two-dimensional axes here, and I just have a point here, and I have another point down here, and so this one is like x1, y1, z1, and this one's x2, y2, z2, like that, and you want to measure the distance, then basically what you would do is you would have to draw a triangle on here like this, and you would have to figure out the length of the sides of the triangles. Now, the length of the triangles, you actually have to subtract, right? Like if this is, if you just think about it, like imagine that this number here is like +2, and and this one here is like -3, right? Then the actual distance from here to here would actually be 5, right? Because it's 3 here and then 2 here. I don't know why I made those different numbers when it looks about even, but whatever. So that distance would be 5, right? If this was at -3 and this was at +2. So when you calculate the sides of the triangle here, I'm just realizing that I'm dumb. There's no z, right? What are we talking about? Sorry. Okay, now that makes sense. So the way you would calculate these is, let me just redraw this for here, x1, y1 for that point. This side of the triangle, the top side, you'd have to calculate it by x2 minus x1 would actually be that distance, right? And this distance here would be y2 minus y1 in that case. Technically, it would be the absolute value of that. But I'm just going to say the way I said it. Okay. And if you wanted the distance then between the 2 points would be the square root of x2 minus x1 squared. That'd be the first side of the triangle there. Plus y2 minus y1 squared. And that would just be the Pythagorean theorem. Okay. Now, when you move this to 3 dimensions, you're actually going to do exactly the same thing. So distance in 3D. So we have our z-axis, x-axis, y-axis. Again, it doesn't really matter how you draw this. Just get the x and the y in the right order. And you've got this point just somewhere up in space, T, and you've got another point somewhere in space. It's hard to know where those are, right? Just hard to visualize those, but you're trying to calculate this distance. And it turns out that you use the exact same formula. It's just going to be, if you've got like Q is x2, y2, z2, and your P here is x1, y1, z1, and your distance is simply going to be square root x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. All right, so it's just going to be the same exact formula. I don't know why I saved that, but I did, so I'll just put it in there anyway. There's your formula. So distance between 2 points in space, it's exact same formula. It's just you don't have this one if you're in 2 dimensions, and you do if you're in 3 dimensions. Okay, so this is all just dealing with points in space. Just how do we graph them and what's the distance between them and that kind of stuff. Okay, so it's easy to use those formulas. You'll have to in the homework, but it's very straightforward, right? They'll just say find the distance between a point. Let's say P1, -5, 4, and Q4, -1, -1, right? How would you do it? Well, we know how to do it. You just write down the formula. So if you're trying to solve this problem, you just start with your formula for distance. So you say distance is equal to square root, and then you fill in all of your numbers. So first thing you do is you subtract the x values. So 4 minus 1, 4 minus 1 squared, plus, then you subtract the y values, -1 minus 5 squared. Now, a couple things to be aware of, right? You have to be very careful to do this in the same order, right? I started with the 4 minus 1 for this one. So I'm starting with the q. So that's my x2, right? And this is my x1. So when I do this one, this has to be my y2. You can't start over on this side, right? Um, I guess technically you'll get the right answer, but you should not. You should do it right. So -1 minus 5, which is actually going to turn out to be a +5, but we have to be careful with the signs. All right, last one, z. So -1 minus 4 squared. And then you just work this out. Now, it's really nice to have a calculator that can work in exact math. You can use Wolfram Alpha. I'll show you what kind of calculator I use actually, just because they're cheap here. Let's go to Amazon, I guess. What do I use? I use one of these. I don't know. I'll have to find it. There we go. This is what I use. So you can see right here in the picture that it's that it can deal with square roots, right? Square roots and fractions, that's what you want it to be able to use. You might have a fancier graphing calculator, but some of the graphing calculators don't do fractions this way, and that's bad. And also, there's plenty of Texas Instrument calculators that work well as well, but they're going to be probably $5 more than the Casio one that does the same thing. So, feel free to pick whatever you want. You just want it to do fractions and trig and square roots. Exactly. So like this one down here, it's probably might be bad. I don't know. This pink one's good. A lot of them are the same, but like in a different looking case. Like I'm pretty sure this one does all the same stuff, a few dollars more. This one does all the same stuff, it's a few dollars more. This is the one that I actually have a bunch of. I think I have 10 of these calculators. It's the same as the pink one, so buy the pink one, because why wouldn't you? All right. Because those calculators just make this like a lot easier to just to type this in. So we will go ahead and work this out by hand though. So we have 3 squared plus -1 plus 5 is going to be 4 squared. Plus here -1 minus 4 is 5 again. It's actually -5, right? But -5 and we're squaring it, so I know it's going to be positive, so I'm not going to write any negatives at all. So this is what we have. So we have square root 9 plus 16 plus 25, which is square root 50. But square root 50 is square root 2 times 25. And I know that the square root of 25 is 5. So this is 5 square root 2. Right? But I don't like doing that by hand, and that's why I use a simple calculator. Okay. Hopefully I did that right. If I did it wrong, that just reinforces my decision to use a calculator normally. I got to close that again, sorry. Every time you sort of minimize it, it gets laggy. Don't know why. Okay. So that is that. Um, what else can we talk about? So we can talk about things that are, some simple graphs. So a few graphs. We cover these in more detail later, but a few graphs in 3D. Okay. So first is a comment on lines. Um, so in 2 dimensions, right? There's only two possibilities if you have two lines. So in 2 dimensions, with two lines, there are two possibilities. The first is that the lines are going to be parallel, right? And the second possibility is if they're not parallel, then they intersect. And maybe there's an asterisk here because there's like a third possibility is that what if they're actually the same line? Then technically, what would you say? Their slopes are the same, but they're not parallel. They do intersect, but they intersect everywhere, so that's weird. So this is going to be two, different lines. So two different lines, they're either parallel or they intersect, right? And you know that that's right, I think. So right, your possibilities are they're either exactly parallel, which I don't know if they don't look parallel there, but you get the idea. Um, or they are intersecting, right? Like if you have one like this and you have one like this, right? If the slopes are different, then at some point they're going to intersect. Okay. Now in 3D, it's actually slightly different. There's three possibilities. And we have a section just on lines and planes where we talk about this in a lot more detail, but they do mention it here in the section, so I'm going to talk about it. So in 3D, there are three possibilities. And same thing, assuming that we're not talking about the same lines. So you could have parallel lines. Now, parallel lines would mean they have the exact same direction. So, so same direction, but they don't touch, and they never touch. I shouldn't say, but they never touch. A second possibility is they do intersect at a point. And a third possibility is sort of like parallel lines, but we don't call it parallel lines. That's where they're not parallel, but they also don't intersect. And we call this skew lines. Okay. And, what do those look like? Well, parallel lines is the same idea in 2D as well as 3D. So if you just draw two lines and you try to draw them in the exact same direction, right, then they don't touch. Um, of course, intersecting lines is going to be where they just happen to cross each other. So you have a line and you have another line. And again, it's hard to see with perspective, but we're saying that they actually are touching right there. But third possibility would be if they just do not touch each other at all. And that would be the case where you have skew lines. So what skew lines look like is, maybe like way up here, you have a line, right? And then maybe way down here, you have another line. And they're not pointing in the same direction, right? Um, like this line right here is not pointing in the same direction as this line, but they're never going to touch because let's say this one's down here in this plane, right? So it's staying on the ground, whereas this one's up in space on the z-axis and it's never going to touch the ground, right? So if like this one's in the ground and this one's up here, they're never going to touch, even though they're not pointing in the same direction. And so that's what we would call skew. This is what we would call parallel. So slightly different because the parallel lines actually have the same direction. Okay. Yeah, so that's just something that lines can do. We haven't even talked about what are the equation of lines, but that's another section. So there's also, we could have planes parallel to the coordinate planes. There's different ways to do that. So for example, if you say what do I want? Like y equals 2, for example, is a plane parallel to the, well, if y equals 2, it would be parallel to the line, or sorry, parallel to the plane where y equals 0. So it's parallel to the xz plane. So what does that look like? Well, if you've got like x there, so no, why did I say x when I drew the vertical line? I don't know. You have x there, you have y there, you have z there, right? So if you want y equals 2, then that would mean over here you have y equals 1, then you have y equals 2, and then right here at y equals 2, that's where you have a plane. And so what would it look like? Well, it would look like this, right? So like if you come up here, go down here, you draw a line that's terrible. You draw a line that's parallel to the x-axis, basically. Something like that. Um, and that would be your plane. And so it's parallel to this, right? This one. So this is the xz plane. And then this one's just shifted over by 2 in the y direction. So this plane and this plane don't touch each other. They're parallel planes, if that makes sense. We don't have a definition for that, but it makes sense. They don't touch because they're, like a sheet. This is like a sheet of paper, and this is like another sheet of paper that's not touching it, shifted vertically, no, horizontally. I think you get the idea, right? So those are planes that are parallel to the coordinate planes. And they're just these planes that we have here, just like if you took one of these planes and you just moved this one that direction or that direction, like that way or that way, or you can take this one, move it that way or that way, and this one you can move it up or down. And those would be parallel to the original coordinate planes. There's not a lot you really have to do with that, but I think in the homework they make you kind of pick it off a list. Like if they tell you, this y equals 2, and you need to figure out where that is in the picture, which picture matches it. It's really easy, but you have to understand the idea, of course. They do have kind of awkward questions here on this. Like here's something they could ask. They could say, it sounds like a really complicated question. Write an equation of a plane passing through. They give you a point, just any point. So like 3, 9, 15. There's a point, right? Passing through 3, 9, 15. That is parallel to the, let's say, x, y plane, right? And so the idea behind this is like, take a look at this example, right? Um, when you want something that's parallel to the xz plane, if it's parallel to xz, then the equation for it is y equals something, right? And that just comes down to kind of your definitions of the coordinate planes, right? Like xy is when z is 0. Well, that z could be something else other than 0, and that would take the xy plane and move it up and down. Xz plane is xz, y equals 0. If you change the y to something else, then you take the xz plane, which is this one, and you move it left or right. Right? So what you would need to know here when you get a question like this question is if they tell you that it's parallel to the xy, then the equation must be z equals something. Must be z equals a number. Well, what number? Well, this one, right? Whatever they said the z value is, that's all you have to do. So it's actually a really straightforward question, but you do have to understand what a coordinate plane is for this to make sense. So then you just say z equals 15, right? So it's the normal xy plane, but if you set z equal to 15, then instead of being like normally this is the xy plane, right? Down here on the ground. But if z is 15, now you come up here to 15, and then you draw that same plane. But now it's floating up in space. This is z equals 0. So hopefully that makes sense. Those are planes parallel to coordinate planes. All right. Next thing we want to talk about is spheres. So in 2D, you have the equation of circles, right? 2D, you have circles. And you even know, hopefully, well, maybe you don't, right? You don't use it very much. But you could have a circle with a certain center and radius, right? Like if you pick a point here, and let's suppose we call this like point A comma B is the center, and then you have a radius around this. So then you have a circle around it. You have an R. This distance is R. Then if you want the equation of that circle, the equation is, so equation, I'm going to write equation of circle with radius R and center A comma B. You probably will be familiar with this equation. It would be x minus a squared plus y minus b squared equals r squared, right? Now, if you want to extend this to 3 dimensions, you're not going to have a circle, you're going to have a sphere, right? Extended to 3D, you get a sphere. And you better understand spheres pretty well before too long, because we use spheres all the time. A lot of times when you're doing integrals and things like that, the region that you're integrating over is like a sphere. So what you got is you got in space, you have a point, but now it's ABC instead of just A comma B. You still have your, it's still like a circular type shape because it's a sphere. Trying to line that up. It doesn't want to. That's fine. So you still have that. Um, but this time there's actually a three-dimensional shape here, right? It's a 3D shape. Still, though, the radius is r. What do you think the equation of that is? Well, it's exactly what you would probably expect. So a sphere with center ABC and radius r is x minus a squared plus y minus b squared plus, you just add the z on the list here, z minus c squared equals r squared. Okay? And actually, this idea comes from the distance formula, which, where's distance formula in 2D? Here it is. So you can actually define a sphere to be all of the points with a certain distance from a center, right? So if you put like, 9 here for the distance, doesn't actually have to be a perfect square. So if you put like 9 here for the distance, you would be saying the distance between these 2 points is always 9. So if you call one of the points xy and the other one ab and put a number here, you get the equation of a circle. And same thing here. You can define a circle as being the set of all points a certain distance from the center. So you just get this kind of thing here in the equation of a circle. This is the distance between x comma y comma z and ABC. And it should be the radius. Okay, so that's the equation of a circle or sphere, sorry. What are you going to do with it? You're going to have to find the equation, or you're going to have to match one up. Sometimes they do a question like this. They go, this is kind of the trickiest the questions we'll get about spheres. They'll say, find the standard equation, I guess they're calling it. Standard equation of a sphere with center. They give you a point, 10, 7, 4. And a point on a sphere is, they give you another point, -1, 3, -2. Right? And they kind of worded it in a weird way too, but that's okay. Now in 3D, what's going on here, I don't really want to draw this very well, I'm realizing, but you just have this point here, 10, 7, 4. I don't really care about drawing it in the right place, so I'm just going to say like, 10, 7, 4, right? Like, so just somewhere. 10, 7, 4, somewhere in space. Erase, erase, erase. Okay. And then what you've got is a sphere. So you draw a sphere around it. I mean, if you care to draw a sphere around it, you draw a sphere around it. Like that. There's your circle basically around it. But then they tell you that this point, -1, 3, -2 is on the sphere. So like somewhere down here, I guess, is another point. And that point's actually on the sphere, and it's -1, 3, -2. Okay. And that's your sphere. Now, how would you actually come up with the equation? Well, you start with your equation for a sphere, right? So we got it right here. So we just take this. Just going to do that for time. So start with your equation. Right? Now, we know that A comma B comma C is the center. So fill in the center. Right? right, which is the ABC. So fill that in. So we're going to erase the A, the B, the C, and we're just going to fill those numbers in. What are the numbers for the center? 10, 7, 4. 10, 7, 4. So 10, 7, 4. So far, so good, right? What you'll realize at this point is we've got the correct center, but we don't know what the radius is, right? So we need to figure out the radius. The way you're going to figure out the radius is you're going to put this in for x, y, z, and that will let you calculate the radius. So, so what you do is you fill in that other point, the other point in for x, y, z, and solve for the radius. Or actually, r squared is all you need. So you don't actually have to solve for r, you just have to solve for r squared. So what's the point? They tell you it is something, what is it? -1, 3, -2. -1, 3, -2. So we go ahead and we fill that in for x, y, z. So we're going to get parentheses x, which is -1 minus 10 squared, plus y, which is 3, 3 minus 7 squared, plus z. Z is -2, -2 minus 4 squared. That equals r squared. And if we calculate the left-hand side, we'll find out what r squared is. So what we got here is -11 squared. Looks like 121. Here we have 3 minus 7 is -4. -4 squared is 16. Positive 16. -2 minus 4 is -6. -6 squared is positive 36. That equals r squared. And then we just add these up together. It's impossible. Those numbers are way too big. Okay, so let's see here. 121 plus 16 is 137. 137, 36. Yeah, I have a math degree. Can you tell? How do you add? 7, 173. So 173 is r squared. If I did that correctly. And then all you got to do now is just write your answer, right? So your answer, the problem, is the equation that we came up with in the previous step here, right? Which was x minus 10 squared. This line, right, is what I'm looking at. Y minus 7 squared plus z minus what? 4 squared equals, and then it equals r squared, and r squared was what we just calculated, 173. And that would be my answer. Okay, so I mean, it's really the same problem as if you were calculating the equation of a circle. You just have this extra bit on there. But probably you haven't actually calculated the equations of circles in a long time, right? So that's why I wanted to make sure I did a problem like that for you. All right. There's one last question before we get to vectors that I think that they have just a little bit weird. So this is kind of a slightly weird problem. Now, the reason I'm calling it slightly weird is I don't think I've seen this in another textbook. Like, I don't know why they're making you do this. It's not hard. They're just making you do it, right? So they say, they look something like this. They say, describe the set of points that satisfies, and they could give you any equation now, right? But they don't. They give you ones that look a certain way. They say something like this, like x minus 5, y minus 3 equals 0. Okay. And initially, if you've never seen this before, it might be confusing. But all you want to do is you just want to realize that you're multiplying two things together and you get zero, right? And this is not something that you're not familiar with, right? You've solved stuff like this before. When you see this type of equation, doesn't that just tell you uh, like x equals 5 or y equals 3, right? You multiply these two things and you get zero. That's what you do here. And then after you write the result, then you just make sense of what that answer was, right? So this is not really anything new or complicated, right? So just recall, like when you solve like quadratic equations, you get stuff like this all the time. So recall, this means x minus 5 equals 0, or y minus 3 equals 0, which would mean that x equals 5 or y equals 3, right? But now the only new thing is that you actually have to interpret this and this in terms of three-dimensional space. So what this says is, so the new thinking is you're going to interpret the results in 3D. So we know that x equals 5. We know what that is now, right? Remember when we talked about planes that were parallel to the coordinate planes? So x equals 5 is a plane parallel to, well, what coordinate plane is it parallel to? See if you can think of it, right? If this is x equals something, then it must be parallel to the other two variables are y and z. So it's parallel to the yz plane. And y equals 3, right? Our other option here is another plane parallel to what? Parallel to the xz plane, right? Just the two variables that aren't being used. So what does this graph look like though, right? Like what does the graph of this function look like? And again, you're not really supposed to be good at this yet, but they kind of are trying to make you start thinking about how stuff might look in 3D. And I think that's just what the point of this stuff is. Um, so you've got x, y, z. So first of all, you've got x equals 5. X equals 5 is parallel to the uh, YZ plane. The YZ plane is this back face here. So we're going to go head this direction, and then we're going to draw a big square here. So like 1, 2, 3, 4, 5. Okay. So like way out here, you've got just this big plane. That is x equals 5, right? And this point actually intersects the plane. It's really hard to see what that looks like to visualize what's going on there, but that's what you have. And then you've got another plane, y equals 3. Well, y is on this axis, so you come out to y equals 3. 1, 2, 3. And you get a plane that's parallel to the xz plane. Xz plane is this one. So you basically take this kind of shape and then move it over to the right, and that's how you'll get it. So like, I'll pick a different color. So it intersects there, but then it's like this. Like that. So these are actually at right angles to each other. It's hard to tell that, but they are. And they actually happen to intersect, and they actually intersect at a line here. Right, they actually cross like this plane that's facing us, and this plane that's at an angle, and there. Okay. And So both of those together make up this equation. I think you just have to pick the picture off a list that matches it. Okay, so I think the last thing we need to talk about is vectors in three-dimensional space, which is why, remember at the beginning of this lecture, and I said it's called like vectors in 3 dimensions, but there's not many vectors. So let me write vectors in 3D now, and I'll write the punchline. Everything is the same as what we learned in the previous lecture. But now, vectors are like this. Like V equals, and now you got your triangular brackets, and now you've got an X, a Y, and a Z. That's the difference. Okay. Other than that, all of the formulas are going to be the same. Everything is going to work identically. So we just kind of want to summarize some of what we know here. So let's see here. So you can do all the same stuff. So example, let's see, find PQ if P is a point in 3D space, 3, 12, 6, and Q is also a point in 3D space, -4, -3, 2. Like, well, how would you do that? Well, we learned how to do it last time, right, in 2 dimensions, and this should be identical to what we did before, right? So the way we did it is we're going to do like EQ, that's the name of the vector. It's going to equal, and how do you do it? Well, this is going to be, this is the terminal point, this is the initial point, right? Same language as before. This is terminal, this is initial. We know that because they drew the arrow, right? P to Q, start at P, go to Q, initial, terminal. And then we know that the way you actually calculate the components is you subtract. So you would do the subtraction here, right? So -4 x2 minus x1, -4 minus 3, comma, -3 minus 12, comma, 2 minus 6. So what's your vector? -7, -15, -4. Okay. So, what would that look like in, 3-dimensional space? Well, we can try to draw it. It's not going to be, again, it's really hard to draw stuff in 3D. Hopefully you're realizing that. But we've got this point P, which is, if this is X, this is Y, this is Z, then we're looking at P is 3 in the X direction, 12 in the Y, so it's way over here, and then 6 up. So if I draw it like this, that's not too far off. 3, 12, 6, that's like that. In 3D space. Then you've got the point Q. The point Q is -4, so that's actually back here on the x-axis behind the YZ plane. -4, -3, +2. So like if you kind of extend this back this way, extend this over this way, you've got -4 is going to be back there somewhere. -3 is going to be somewhere over here, and then +2 is going to be up here somewhere. So you got this point here, that's your Q, -4, -3, 2, like that. And then you've got this vector that goes from P to Q. So you just draw it starting at this point, and then it heads this way. That's the vector from P to Q. Right? So everything is the same as the previous section, but harder to draw by quite a bit. That's really all that's going on. Let's see. Let's write out the formula so you can have them written. I need to post a typed up handout with this stuff, but rules for vectors. So we got a vector v now is x1, y1, z1. We're going to have a vector w with a hat, x2, y2, z2. We're going to need a scalar, k, a scalar, which remember, scalar means real number. So we know we have our operations, right? So like kv is defined to be the vector kx1, ky1, kz1. That's scalar multiplication. We know how to do that. We know how to add, like v plus w is the vector. You just add the components, x1 plus x2, and so on. x1 plus x2, comma, y1. So hard to write things, plus y2, comma, z1 plus z2, right? That's vector addition. Subtraction is identical. I was going to say that I wasn't going to type it, but I am because I can copy paste it and then you just change the sign. Right? Minus, 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 minus. Vector subtraction. Okay. We can do the magnitude. Technically, we haven't done that yet. For 3D, the magnitude of a vector, it's going to be basically the same formula as you used before. X1 squared plus y1, I don't know why I wrote it 2, y1 squared plus z1 squared. That is magnitude of v. Magnitude of a vector. And then you can find the last thing we'd ever wrote, but we can do a unit vector in the direction of v. So how do you do a unit vector in the direction of v? Well, it was if you take the vector v and you multiply it by 1 over its magnitude, right? Remember, like, if you calculate the length and the length is 5, then what you need to do to get a unit vector is divide by 5. If you divide a vector with length 5 by 5, you get a vector with length 1, right? Length 5 divided by 5 is 1. So this is what you do, which they write different ways. You could write it this way. x1 over the magnitude of the vector, comma, x2 over the magnitude of the vector, x3 over the magnitude of the vector. That's how you would do it. So that's a unit vector. And also remember that if you wanted to calculate a vector with like length 7, what you would do is first you calculate the unit vector and then you multiply by 7. Right, unit vector has length 1, and then if you multiplied it by 7, it would have length 7. So that's how you can get a vector of arbitrary length. Let's do one question here. I'm not going to do like vector addition, but what I will do is, so let's say I say let v equal -2, comma 9, comma 5. And I'm going to say find a unit vector in the direction of v. Okay. And so when you see this, find a unit vector, I like to break it up into 2 parts. Like I don't start with this, I start with this. I'm just going to calculate the magnitude. Right? So for my answer, I calculate this first, the magnitude of the vector first, that's the length. So I go magnitude of v is square root -2 squared plus 9 squared plus 5 squared. So it's square root 4 plus 81 plus 25. I mean, why do I have to add? Why is my life so hard? Okay, 81 and 4 is 85. Is this 110? I feel like this is 110. Okay, let's say it's 110. Then what you would do is you would try to, if you can simplify that, do so. Again, this is why you want a calculator that can do stuff like this. If I'm trying to do it myself, I would say, okay, that's 2 times 55, which is 2 times 11 times 5, right? Okay, so that doesn't have any, so that doesn't simplify. So square root 110 is just square root 110. So then the unit vector is 1 over magnitude v times v. And so that's 1 over square root 110 times the vector v, which was -2, 9, 5, right? Yeah. So that's it. You just write that. And if you want to, you can kind of distribute this and put it under there and have -2 over square root 110, comma 9 over square root 110, comma 5 over square root 110. Like that. Okay, now something to keep in mind is that I did not rationalize the denominator here, but you always have the option of doing that. It's just, do you want to? I mean, I don't know, right? You could, but I wouldn't necessarily bother. You could rationalize the denominator by doing like this, right? Like multiply by square root 110 over square root 110 on each of those. So if you do that, you would get -2 square root 110 over 110, comma 9 square root 110 over 110, comma 5 square root 110 over 110, right? And that would be the same thing. And you could simplify this one, but I'm not going to. And this one, but I'm not going to. That's already too far. I would leave it like this. Honestly, this is what I would type in to the computer. Actually, first I would try to type this in because it's less typing. And if that didn't work, then I would type this in. And I really doubt that it would make me type in this, but I would be prepared to do it if I had to. Okay. Also, just a comment here, I guess. When you do this magnitude of a vector and then a unit vector in the direction of v, you're not allowed to divide by 0, right? So this is assuming that the magnitude of v is not 0, which only happens when you have the 0 vector. So this is assuming that v is not the 0 vector. Not the 0 vector. So if v is 0, 0, 0, you can't find a unit vector in the direction of 0, 0, 0. That doesn't make sense because 0, 0, 0 doesn't even have a direction. Okay. So I think we are done here. That was a pretty long lecture. So yeah, I think we're done here. Go ahead and work on the homework. Homework's pretty easy. I think I will post a video where I do some of the homework problems, but I don't think it'll be too much of a problem for you guys. All right, so that's it for now. I will see you in the next video.